everybody. All right. So welcome to the webcast, and the webcast is called "Don't Stress Out Over SOLIDWORKS Simulation. Just Get into Contact." I don't know how they want us to say that, so it's pretty funny. So I think you guys are expecting me to know. So, but you guys are here to learn about contacts and simulation. We'll go ahead and get started. Let me switch over to my presentation screen. I just wanted to say a quick hello to everybody and welcome you in. Let me switch on over here. Hopefully it'll help with bandwidth as well. All right, so just a little bit about myself. I guess let me formally introduce myself to everybody here. Let me switch on over here. So again, my name is Enrique Garcia. I am one of the application engineers and simulation specialists at DASI Solutions. I've been doing this type of job for going on 12 years here in a couple weeks, and I've been doing technical training with SOLIDWORKS, simulation. My background's in biomedical engineering from Arizona State University, and been really involved in teaching and sharing my knowledge with people just over my whole career, and it's kind of a tendency of mine. I just like to share what I know and collaborate. Part of it was working with Agua Fria High School Band of Owls here in Arizona and Avondale on the west side of the Phoenix region, and worked with some fantastic kids for a lot of years, and it was a blast. And a little bit about myself, have many nieces and nephews, and I have a robot dog. And just because of all the nieces and nephews, I've now become the family toy maker. So I've been picking up some 3D printing skills and just trying to join some maker communities and just doing projects and things. So I've always been asked what are some of the projects I've been working on. So I just thought I'd share a little bit about myself. Here's the Moana Heart of Tafiti necklace that I made for a niece, and then I also made one for my sister for some cosplay. So my sister did the finishing work and the necklace on that. So, a little collaboration, all done with SOLIDWORKS. My nephew Jack, he's 5 and he loves Spider-Man. So he wanted some web shooters. So I made him some web shooters and some replaceable cartridges and glow in the dark and the whole bit. And he was ecstatic and put on his Spider-Man costume and jumped on the kitchen table in one shot, just like CrossFit. So he was he should join a CrossFit gym. Here's my robot dog. His name is ISO, and he's quite old. He's going on 19 years, and he's old enough to vote. He took a spill last year, and I was trying to repair him. I couldn't source parts for obvious reasons. It's quite old, so I did some reverse engineering, some optimization with simulation, and some testing just to see if this print could hold up. And so far, so good. He's running strong for being a 19-year-old pup. So. Again, just some projects and some things that I've been using SOLIDWORKS. We try to keep sharp here at DASI Solutions. We work on projects, consulting, and just to be able to give everyone the most accurate and definitive answer for anything you may need. Also, I forgot about this one. In case you didn't know, the Tamagotchi is back. For those of you that didn't know what that was, if you experienced the 90s, if you're a kid of the 90s or lived through the 90s, you probably saw these things around, virtual pets, and yeah, we had good experiences with them growing up and had them confiscated in school and all that deal. So got some for the wife and I, and we made ourselves some watches. So you can see me wearing them as a watch. So again, just projects and just some things that we've been working on here. All right, back to the presentation. So here are some of the topics. Again, the goal here is to cover simulation contacts, and strictly contacts. I think, yeah, here's some of the topics that we're going to be introducing and touching on. But ultimately, the goal is going to be to give you a very good foundational knowledge on contacts, some governing rules that you can go by so that when you have simulations, you'll know how things kind of play nice with each other. That's the goal. And then just fill in with some of the other bells and whistles we have related to contacts. So here's a little introduction. Again, the goal is to give us a good foundational information on contacts. And it is, in my opinion, and I think in a lot of analysts' opinion, it's one of the most important parts of a simulation study. This can break or make your simulation. It can throw off your results. It's the most important part of a setup. It is also can be one of the most time-consuming if you have a larger assembly, a lot of faces that need to react and interact with each other. That's it. And in all honesty, being in help desk and doing fielding tech support cases, after reviewing tech support cases, reviewing contacts seems to be the common denominator. Going in and reviewing how things interact with each other, then we get the light bulb. Okay, this is what's going on. Running the study again, and now getting a more expected or ballpark figures to what you're expecting from hand calculations or from empirical testing. If you did some prototyping and testing, now it maybe starts pointing in that direction. So context again, and I think that's why I'm preaching to the choir here. Everyone maybe understands that this is very important to us all. Some other things that I get asked usually is going to be, Enrique, I've spent the time and I've mated this assembly up with all these mates. Is it possible just to go in and just connect all those mates up in SOLIDWORKS contacts? Is there like an import or a port functionality to simulation? Unfortunately not. I believe I've seen some enhancements on that. I can't recall off the top of my head now, but I have been asked that for quite a bit. But unfortunately not. There is no link to it, although it is a good idea to go in and review your mates just to get an understanding, if you're not familiar with the model, of how the model should react. Again, if you're not familiar with the model, but it's a good practice nonetheless, and then go back and try to emulate what you saw there with contacts and simulation. Now, all the contacts and items we're going to be dealing with in this presentation will be inside of the SOLIDWORKS design tree under the connections folder. That's where we're going to be applying our contacts and looking at most of these settings from that region of the model. Again, this is a very distilled and basic study or presentation on contacts. Before jumping into a simulation and doing contacts, I do have some tools I want to share with you guys of how to approach contacts and simulation. Let me give you a scenario. Let's say you get into work in the morning and your boss or your higher up says, hey, I want you to work on this project for me. Here's the model. Would you be able to give me some simulation results by lunchtime? You want to say yes, of course, but again, the bottleneck and the time invested is going to be in contacts most likely. So there's some tools I want to show you. First is the interference detection tool. This has an option to detect coinciding faces, so you can see how many contact or face pairs you would need to address before you run a study. So we'll be showing that here shortly. And also a couple years ago they released a similar utility that's baked in to the simulation, and it's accessed through, again, the connections tool, and it's the contact visualization plot. And it does a very similar thing as well, and it's to detect and to understand what we're working with as far as time for setting up simulations. Let me jump over to SOLIDWORKS here. I want to show a little bit of how these two tools work. So the first one is done outside of SOLIDWORKS, and it's the it's the interference detection tool that can be accessed from the tools menu, or it can be accessed from the evaluate tab, and we'll go to interference detection. Now, a good practice, now that I'm thinking of it, actually, let me ask some poll questions here. I think it'll be good to kind of hear everybody and see where everyone's at. And I do have some questions for you guys. Let me launch a first poll here before we dig into the contacts. So the first question here is going to be just asking about just your experience level with contacts. If you guys can take a minute or so just to answer that question, much appreciated. I think we've settled down there a little bit. Give you another couple seconds. All right, let me close out that poll and let's share that with everybody. So it looks like a good amount of you guys have no experience, so that's exactly what we're here for those that have no idea or are starting out with simulation. And you're an analyst and you're wanting to know the tools. 50% have little experience, so that's perfect. And I have a decent amount too, about 20% of y'all that use them and maybe are wanting some best practices and things. So I think we got everyone covered. Very nice. I have one more question for everybody, and this is relating to interference detection. So let me do one more poll here. So the question is, do you check for interference before starting your simulation studies? So I'll give you guys a minute or so to answer. All right, I'll go ahead and close up the poll here, give you a couple more seconds. All right, let's close her up. And let's share that. So looks like, yeah, a good 15% of you guys always do it. Some of y'all do it sometimes, and a good amount of you guys love to live dangerously. So a little Austin Powers for you there. So you'll have to live dangerously. So let's talk about interference detection and maybe just a best practice with that before we go into the coincidence tool. So let me switch on back to SolidWorks. And so it's good. It's good that we're thinking about interferences because when you're working with a simulation, if you haven't addressed that and you set up your contacts or let's say you want to go in and do a mesh of the model, you may run into some meshing issues. SOLIDWORKS likes to transition the mesh from one part to the other, and if there are interfering bodies, the software won't know how to connect the nodes between one boundary to the other, and you may have some errors or some issues with simulation. So so yeah, that's the negative or the con to it. Also, when it comes to contacts, if you set all your contacts up and then you go in and you address in the SOLIDWORKS model, you make changes to faces and face definitions get changed or geometry gets cut off, you may need to go back and re-edit a lot of your contacts potentially. So again, it takes a lot more of your time overall and your efficiency in setting things up. So I recommend just jump in there and do a quick interference detection like maybe we'll do here. We'll just do a little calculate, make sure there are no interferences in the model, and then you can move on forward with your contacts. A little comment on the models that we're going to be working here. Definitely, I understand they're very basic. I wanted to just kind of get away from referencing any certain application just to make this as general for everybody. All of these concepts are useful for every application that we have in simulation and industry. So just a little comment on these models that you're going to see. They're very rudimentary just to get the message done because contacts can be complicated. So let's talk about this utility that we have, or this tool that we can use to detect contacts. Now that we've verified that there are no interfering bodies, I can go in under Options and turn on Treat Coincidence as Interference, click Calculate, and I can now see this list of all the different phase pairs that I will potentially need to address in a simulation study when I do contacts. So again, if someone asks you, hey, can you get this done by a certain amount of time, if you take the amount of contacts or phase pairs you're detecting, multiply it by how many seconds it takes you to do a contact, you can get an idea, at least for that phase of the simulation setup, as to how long it'll take you to kind of get some things done. And again, always plan for runtime and some miscellaneous troubleshooting just to set expectations, but that's a great tool to use. The other tool is the contact visualization plot, and that lives inside of the simulation. So this is done, I would probably do this maybe at the beginning, and I would just jump into the connections folder here to initiate it. You do a right click, and you'll go in and you'll choose contact visualization plot. So again, it looks a little different, but this is the in-house or native tool for this, the official tool for it. So I would go in and I would hit calculate, and again, very similar behavior. You would go in and get all of your contacts that are going to be detected there. Another positive with this is if you've meshed the model, you can also detect solver-based contacts. These are potential faces and potential collisions that could occur due to solving the model, applying a force or applying a prescribed displacement, and it can also detect those edges or faces as well. So this way you'll know that in addition to these static or initially touching faces, you'll need to address other geometry with contacts as well. So that's the positive or the plus on the contact visualization plot. So let's talk about these different contacts next. So the three major contacts that we're going to be discussing in today's presentation are bonded contacts, no penetrating contacts, and allow penetration. So bonded contacts are just like you would think. You're going in and you're taking faces that are maybe going to be touching or faces that you're going to want to force a bond between, and it's essentially a weld. You're causing this to be fixed onto the other item, and that's done by applying this bonded contact. The other is quite the opposite. The other is your no penetrating contact. And this for faces that are being assigned to this or components that are being assigned to this will respect each other's geometry or faces. Again, so you can get reactions off of them. You'll have faces that slip past each other and deform against each other, all what you would expect with no penetration. And then you have allow penetration, which honestly for a long time for myself kind of baffled me as to why you would want to allow faces to penetrate purposefully in a simulation. It sounds counterintuitive, and I did stray away from that for a long time before I understood it fully. And the reason for this is when you have complicated contact problems. Think of an example. If you can visualize your hand and you're putting your hand on a table, on a flat table, you're pushing down on the table, and let's say that's your simulation study you're trying to run. Well, your hand has a lot of complex curvatures, facets, and when you're, let's say, applying to all those little curvatures and small faces, you're applying a bunch of no penetrating contacts. When you're running the solver and you're trying to converge a result, it's maybe too much for the solver, and then you may get some sort of solver error saying that it's too complex, something of that nature, and you may have to do some troubleshooting. So that's when allow penetration, at least in our practice, comes into play. You can take maybe the majority of those no penetrating contacts and switch them to allow penetration just to simplify the model and just keep a couple of key players of contacts that are no penetration so that you can get something that runs. And at that point you can slowly go back and edit those back from allow penetration to no penetration to kind of get a happy medium between performance, something that the solver can run and solve for a complex contact problem with bringing some of those allow penetrations back to no penetration. So again, just good for troubleshooting. That's been our experience with using, my experience with using this tool or that particular contact type. There are some additional contacts that are kind of offshoots of them. I'm not going to dwell too much on them, but they include some thermal contacts that we can have, like insulation, and there's some self-contacting options that was added a couple years ago, which will allow one body to go in and detect its own penetration, so it'll have a no penetration on itself. This is great for springs as well. That for the longest time we've had to use some time-intensive workarounds, but now with the self-contact options, we're able to be able to self-detect contact, which is nice. Let's talk about, now that we've established these three contact types, this is the part that gets tricky and the part that kind of intimidates a lot of us new analysts to the tool, and that's how these contact types play nice with one another. And so there's three levels or three ways that we can apply contacts to a simulation. The first, the one that I want to mention is going to be a global contact, which is, unless otherwise specified, the software will go in and just assign a global bonded contact to everything. This way, in case you didn't need to locally assign or individually assign things, you can just run with that. A second way of applying contacts is a component level contact. If you have two parts that you know are going to be interacting or colliding with each other in a calculation, you don't know exactly how they're going to come together, then you can do a component contact and choose two part files or two solid bodies, and you can assign a contact to it. The third way is a local contact. And if you have an idea of which faces are going to be contacting with each other, then you can specify those very specific faces, edges, points, and specify one of the three contact types. So those are some of the ways that you can apply these three contacts. Now the gotcha, I think, and something that really is not very apparent when it comes to working with simulation contacts is that there is a pecking order. There is a contact hierarchy to be aware of. So depending on how the contact was applied, if there are two contacts competing for the same region or the same geometry, one will be more powerful than the other, and one will respect the other's rule more than the other. So let me comment a little bit about that. So you can see here, this is the pyramid, the contact pyramid. For those of you that have been in my classes, that's something straight out of the manual there, this little contact pyramid. And that's the order of priority level going from the bottom of the base to the top. This next page, I just kind of boiled down the more common rules and the experience that you're going to get with contacts in general. The first one is that there is always a global contact set by default, and it's always set to bonded whenever you start a new simulation. You can only have one global contact per simulation study. If you try adding a second one, it'll give you a little pop-up message telling you can't do that. Let's see. Oh, here's one. A gotcha is going to be a big gotcha for new users especially, is that whenever you have a bonded global contact, this rule will only be applied to initially touching faces in the simulation. So if you have a model and faces are touching, it'll do bonds for those, and if you apply a force or a load of some sort and geometry changes and starts to interface with each other, those components that are going to collide will not, because it doesn't know any better. It doesn't know the rule. When it first started calculating, it didn't know that that geometry had a rule to it. So you would have to go in and either apply a component contact or a locally applied contact on those expected faces to react or interface with each other. The last three here that we have are going to be your just kind of putting down in words the tree. You can see the kind of general rules of what is being overridden by what, and that's a general sense of what's going on here. Again, this is there are some nuances and things that as you start playing with contacts, you're going to find that some of these will compete in a little different way, but overall the goal is to give you a good foundational knowledge to then go in and explore this this discipline of contacts on your own and learn some of the other nuances. All right, let me jump over to SOLIDWORKS again, and I want to cover how these are added, and I want to show you some of these hierarchical rules that we have to the model. Let me open up just this very simple model here. We have three parts, and we're going to just start a new simulation, and we're going to be going through those three levels of contacts. We're going to start with a global contact, a component level contact, and then a locally applied contact on some specific faces. So I'm going to start by creating a new simulation study, new static study, and I'll do just some setup here. And I want to point out that under component contacts, this is the connections folder where we apply all of our contacts. When you do a right click, we're going to be focusing on the component contacts, and the locally applied contacts are added using this option. So you'll notice whenever you have a model, you'll notice that has multiple bodies if it's a part file, or multiple components if it's an assembly, you're going to get global contacts to show up there, and it's automatically put in. If I edit that, we can kind of see under the hood of how it's implemented. So it's defaulting to bonded. It's just checking the general top level assembly, and it's checkboxing the earmark to tell it to be a global contact. So that's automatically in place. I'm going to finish setting this thing up here. I'm going to stabilize the model. I'm going to apply an external load to the top here of my geometry. Let's do pounds here. Again, I'm purposefully putting in a very, very large load. I know I'm going to be going past the yield point of the model. I want to just make sure that I can see a lot of displacement here. We're not going to rely on the stress values. We're going to look at the overall deformation of what's happening to the geometry to pay attention to the contacts. Good practice is to just go in and just do the mesh. I like to do this as a separate item. There's my mesh. And we're going to run the study. I'm going to go in and just go ahead and run that. So it ran, and this is what I'm expecting to get. So again, we have a very large load assigned to this model. So it's telling me that I have excessive displacements. We understand that. We are not going to let it run with a large displacement mode. We want to keep it with the linear material and contact model here. And so at that point, I'm going to look at my contacts here of what's happening. So I can see here that I have some interference, right? As we mentioned earlier, the global bonded contacts are taking care of the connections between these items, and for all purposes this is acting like a continuous solid body. The only difference that could change is if the components were made out of different materials, then the material properties would change and shift as you're going between those, but they're essentially welded, face-to-face welded together. Now when you're dealing with large displacement like this, it's always a good idea to change your deformation scale so it's a true scale. So I'm going to edit the definition of this plot I'm looking at, and we'll go in and we'll change that to true scale just to confirm that we do have in fact some interference that's occurring there, and we can see that. So now that we can confirm that we have a true deformation scale, I'm going to go in and add a no penetration component level contact. So for this I'm going to jump over to connections. I'll go down to component contact. I'm going to switch the type to no penetration, and for my selections I'm going to pick the two components that are going to participate in and interfacing with each other. And it's telling me here that I need to go in and remesh the model, which makes sense because when I'm changing contacts and contact definitions, the nodes need to rearrange themselves. Whenever I have geometry that's going to be interfacing, you're going to have equal and opposite calculation nodes on each surface. Instead of with a bond is going to just share nodes across those boundaries, whereas no penetration contacts will have to have its own node on its own part to be able to react off of each other and get reaction forces and interrogate the model that way. All right, so let's see. We have added we have the global contact that's going to still participate, and we're going to specify now a component level no penetrating contact. Let's go ahead and mesh the model. It's telling us here we need to remesh, and we're going to run the study again. Now to give you a little heads up, now that we have no penetrating contacts in the mix, the study will take a little longer to run. Let me bring this over here. So usually at that 27%, you may, if you're familiar with the simulation, you may have seen that it pauses there for quite a bit. If you hit the more, it's usually resolving its contacts and its reactions to the study at that phase. So there it is. And at that point now we can see that we're climbing up that pyramid, contact pyramid, and now we're respecting that geometry there. So there's the component level contact. Let's go in and let's switch that now to a local contact just to show that that's also going to take priority. I'm going to go in and for this component level contact, I'm going to go in and just suppress that, and I'm going to replace it with a locally defined contact. So I'm going to right click on the connections there and access contact set. Under type, I want to leave it no penetration, and then pick my two faces here. Notice that we have friction as well, so we have a static friction we can apply depending on the material surfaces, geometry. If there's lubrication involved, you can specify your coefficient of friction. There's also a little gap section in case you're modeling with gaps, or which we'll talk about in a few minutes, but just to kind of show you the rest of the interface here for a no penetrating contact. For us, we're just going to be applying, and we're saying to go in and respect those two faces from penetrating each other. Click OK. Let's mesh the model, and we'll run the study just as before. Now, we're going to get this warning here. This warning refers to some settings we're going to talk about shortly, but just to kind of give you a heads up, we have some advanced contacts that will help simplify no penetrating contacts. But yeah, that's just what the warning is mentioning. I'm going to say yes and let it continue on, and we will be talking about these contacts here, these advanced contact settings that I think are important just to know about. All right, so just as before, we can see that now we are still respecting that contact. It's not a component contact now, it's a locally applied contact. So again, I hope that kind of illustrates what's happening and how you can add contacts. If you're new to adding contacts, those are the three you should be focusing on. I mentioned that there are some additional contacts. I just want to touch on them really quickly so you just know about them and what they do. If I go into my locally applied contacts, I can do a self-contact in case I had maybe like a clip or something, a paper clip, something that kind of just loops around itself. I can then choose the whole body and turn on self-contact so that when I do apply a force or something to or load, it will detect itself. Before, you had to do some workarounds, and you may be using split lines or split the part completely so that you have two separate parts to deal with before this option. Some other advanced or some other additional contacting types is the virtual wall condition. This is, again, if you're wanting to idealize geometry or basically replace geometry with a model in simulation, I can use a plane, and then I can specify a face that will react to this pretend or virtual wall, or that will be represented as a plane. So you'll choose the face, and then you'll choose the plane reference. It has to be a plane reference. You cannot use just a surface body or another dummy body for this functionality. And again, it helps prevent having to remesh additional geometry, and it saves on resources. You also have shrink fit conditions, which what this will do is this allows you to have geometry that maybe needs to be compressed. An example I can think of is if you're modeling the reaction to a seal, perhaps on maybe like a cover of some sort, or like an oil pan, and you're torquing down on the oil pan, it's compressing the seal. Well, you can model your seal and your surrounding geometry as it would be uncompressed, and there will be some interference. And with this tool, this allows you to take two faces and allows them to be coincident or touching. So it allows the that seal to be compressed by forcing those faces to touch instead of interact with each other. So again, just to touch on that, we may expand more on that maybe in future webcasts or presentations. We're definitely liking this series of simulation, and we plan to do a couple more, so that may be something for a future webcast. But just so you know about these settings, those are some of the other contact types we have available. All right, let me switch over and let's talk more about contacts. This time, let's talk about addressing these gaps and clearances that can exist in geometry. when you're designing your models, perhaps you have clearances between parts if you're modeling for weld gaps and in your weldment structure, or if you're modeling something and you don't want to or don't need to include excuse me, and you don't need to include the seals, I guess that's an example that we talked about earlier, or filaments of some sort, and there are small gaps to account for that spacing. In simulation, you can go in and respect those small gaps. So down below, I try to show that the different levels of contacts, and I wanted to show that you can apply and respect gaps only with two instances here. You can apply them with locally applied bonds and no penetrating contacts. So with a locally applied bond, the way that works is you, if you have a model with a gap and you apply a bond between them, the software will say, okay, I'm going to just keep those frozen together, and they will be bonded, and we'll assume that there's a very, very high, very, very tough material that's linking these two components, and they will be bonded together with whatever is in there. It could be weld or something as an example. Let me show you that here with this model actually. If I jump in, I can take the no penetrating contact, and I can just switch that out here, and I can switch it to a bond. Now because it's bonded, yes, we're going to do the mesh again. Now because, let me hide that plot. Because it's bonded now, it's going to have a direct connection from all these nodes to this bottom node, and it'll freeze or leave that gap there in place. So let me go in and we'll do a mesh, and we'll run the study just to show that it's not going to move and it's going to respect that bond there. Now again, because we don't have no penetration, the run times are much quicker because it does not have to calculate the extra overhead of slipping and potential friction and items. So here it is. So it's pushing down, and there is no, you can see my deformation scale is true scale, so there's no exaggeration of the movement, and we're not closing up that gap. It's respecting the gap using this locally applied bonded contact. Now, if your geometry is more complex and you don't have a bond between them, but you do want to respect that gap, maybe you have a washer, a spacer, and not a weld in between these faces that are going to bond them, but you do need to respect that gap, and you need to have a reaction forces acting on the geometry, then you can use no penetrating contacts, and you can use that gap clearance option that I showed a little earlier. If I were to go into that locally applied contact, this guy here, and say no penetration, this region here is what we're going to be talking about. So I'll be the first to admit the verbiage on this on what these options mean is confusing. For years, I would have to go back to my notes and my manuals to go back and remember what the setting is for when to respect the gap and not close it, or when to allow it just to close. So the verbiage is always ignore clearance, and that means that with those two faces that you've chosen, always respect that gap. Do not let it close. That's the first option for always ignore clearance. The second option is ignore clearance only if gap is less than whatever you type into the fill-in field. So again, that is meant for if you're selecting maybe a family of faces, and you have like the keep visible tab thumbtack on, and you're applying multiple face pairs, and you just don't want to mess with saying, okay, ignore this clearance or respect this clearance. You can give yourself a little cutoff, and if it's less than a certain amount, it will respect the gap and not close. If the faces are spread out wider than that particular cutoff, then it'll just close it right back up during the calculation. So I made just a little example just to kind of talk about this a little bit more, because it can be confusing. Just speaking of it, I want to show just this little illustration just to show an example. So I have just a fixed plate a base plate down below. I have another component with some sort of force F pushing down. We're assuming that we have proper constraints so that the model is not unstable, and it's going to push down and let these faces close or respect. So let's say that I'm going in and I'm applying contacts here on these faces, contacts on the other side of faces, and I've chosen always ignore clearance. If I choose always ignore clearance and I run the study, those gaps will remain as they are, a 3-unit gap, a 7-unit gap. It will not close up. If I switch the option to ignore clearance only if gap is less than, and let's say I enter 4 millimeters and I run the study, the model will run and it will respect the gap that's less than 4 millimeters, so it'll respect the 3-unit or 3-millimeter gap. But the larger one, it will close. So we would expect this to close up and then start to react off of each other, and we can see stresses develop after you've made contact or slid a little bit and made contact fully. So again, not very commonly used, but just again, we're doing this presentation, and I wanted to just talk about it so that everyone knows what the tool is for in general. Let's talk about some more advanced techniques now at this point, so that we can know a little bit more about contacts. So this is more maybe to maximize or be a little more efficient at adding contacts, and this is adding contacts to your model automatically. So we know we have face detection tools or coinciding faces. We can also do a proximity detection if you are modeling with gaps in your design, and we can use this utility to detect these faces. This is the interface that we're going to be looking at in our examples shortly, but we can switch it to an automatically find contacts, choose to detect touching faces or models that have gaps in them. We can pick certain components if I wanted just to apply contacts on maybe 2 parts that are a little complex and you wanted that to do it automatically, or like in our example, we're going to do the whole assembly. I can then choose the whole assembly and say find contact sets. It's going to then list every single contact detected. We can specify the type of contact, and then we can apply them one at a time. It'll highlight them, or what we're going to be doing is we're going to mass select all of them and add 15 or 17 contacts all in one shot by clicking the plus there. So let's take a look at that next. For this, I'm going to open up a model here. All right, so I'm going just to start. I'm just going to do a partial study here just to show this, this functionality. And I'm going to jump into connections. I'll go to contact set and then make the switch here under contact from manually select contact set to automatically find contact sets. Choosing contacting faces. For the selection box, I'm choosing the top level assembly, and I'll click on find contact sets. Down below, you're going to see that we can click on individual contacts. It's going to give us some highlights, and we can specify the contact type, and we can add them one at a time by clicking create contact sets. If I find one that maybe isn't going to be used, then I can select it and I can click to just delete it from this list and move on, and then maybe do something else. Maybe that's a bond or something else, or maybe it's going to be connected with virtual fasteners or another way of connecting options. Or I think the power behind this is I can do a shift select, and I can select all the contacts, specify the type, and then apply them all in one shot. Forgot one there. In the end, these contacts they work just the same as before. I can go in, I can edit them individually. They are, as a good practice, they've split up the contacts individually. So for troubleshooting purposes, I can go in and suppress them, rerun my study, see if that caused the error, if I ran into an error. If not, you can bring them back for troubleshooting. But that's how you apply contacts automatically in simulation. Again, very powerful tool. I recommend them as long as you do go back and you vet out that setup. Don't just let the software figure things out. If you're signing off on these results, I would recommend going through and at least skimming through all of these to make sure that you're addressing the proper faces. All right, let me talk about an advanced setting that we have with contacts, and this is specifically for no penetrating contacts. No penetrating contacts can take the most time to calculate, especially when you're dealing with component contacts, because it has to go and it has to interface and touch different surfaces and figure out potential interactions with between components. And so if you're running out of RAM resources or you're running out of time for this, you can simplify the no penetrating contact by using some advanced settings on the down below here. So these advanced settings have to be turned on. Let me show you how that is done. I'll just go over and we'll go to the simulation menu in SOLIDWORKS. We'll go down to options. We're going to go under default options, click on the mesh category, and we'll turn on show advanced options for contact set definitions. So once that's on, now you can go back to your contacts and do a mass select of contacts or just edit them, and you'll have the option to turn on advanced and to simplify those contacts. So there are 3 options for these contacts, and depending on what your circumstance is or how you know these components or faces are going to be interacting, you can simplify by using an advanced setting. Let me talk about the simplest one and the one that takes the least resources, and this is the node-to-node advanced contact set. For this, you do have to use a standard mesh. You have to use a compatible and standard mesh. Basically, the nodes between contacting faces need to align. You need to have an equal and opposite node between one component to the other so that they're perfectly in alignment. And these faces have to be initially touching. So if you have a scenario where you have gaps, you cannot use a node-to-node contact type. You have to make sure that they're touching initially. The faces can slide a little bit, but again, that's kind of subjective. I would steer clear of that. And the faces cannot separate. So if you have a geometry that needs to shear off of each other or deform off of each other, this is a very simplistic form of it where the faces will not separate. So you will get a little bit of a skewing of your reactional forces there because of the simplification that you're making. The second option is actually the default. So if you don't have advanced on, it will default to this node to surface option. And for this, faces can be initially separated. They can, within the course of the calculation, come together, slide using friction coefficient. However, they cannot re-separate after they initially touch. So that's the gotcha or the simplification for that, and that helps save resources on that calculation. The third is your the most realistic and your most accurate. This allows you to have initially not touching faces. You can come together. You can slide all you want. You can also fully separate if the simulation calls for it, or a partial separation because of a deformation. All of what you would expect is included in the surface-to-surface contact. So that's what they're about. Now that we've talked about these advanced contacts and what they do, I mentioned that the default is this node to surface. If you don't have the advanced on, it'll just default to that. And that, again, will not allow you to separate or have a partial separation of the model. So if you wanted to default to the surface to surface, the one that does allow you to separate, or the more accurate response, there's an option I wanted to share with you, and this is under the properties. And this is under options, and it's located under the gap contact. It's called improve accuracy for no penetrating contact surfaces. And as long as that's on, any kind of contact that you apply will respect and will use the surface to surface contact unless you specify locally. So if you go into those others and you go to advanced and you turn that on and you override that with something else, it'll just use that. So that's kind of how that works. Again, it's a more advanced setting, but for those of you that have been using this for a while, it's just good knowledge for everyone in general. All right, let's go on back. I know we're getting close to the end of our time here. I'm going to wrap up with just some tips and tricks, and we'll have some time for questions here in the end. I appreciate you all that have been here, and I don't think I see any questions at the moment, but we'll have definitely some time here after we're done for some questions. Some best practices and tips. I've commented on a couple of these, but just to reiterate the importance of them, the no penetrating contact sets, if they're a component level contact, that particular contact combo is the most computationally expensive. It takes the most time to run. I see this in tech support and help desk quite often, where a model just takes so long to run, and I get a message saying, hey, this model went from pretty simple to run to taking 5 hours. What's going on with it? And we look, and there's a lot of no penetrating component contacts that are applied. Reason this takes so much time is because we have these parts, and the software has no idea how they're going to interact with each other, so it has to cover all of those combinations, so when it does touch, whatever winner it is, it knows for sure it's going to be able to react off of those. So again, it's over-calculating because it does not know what it doesn't know, so it needs to calculate all the different potentials or be prepared for all the potential collisions for contacts. So that being said, avoid component no penetrating contacts unless you really just don't know how they're going to interface, and then that's what it's for. If you have some idea that face A will collide with face B, then just apply a local no penetrating contact to help save that overhead. We talked about the next tip earlier, earlier in the model or in the presentation. Resolving interferences in the model is a big plus. This way, if you do not do that and you go in and you apply all these contacts and you realize you have interferences, and you go back to the CAD model and you make changes to faces, Simulation and SOLIDWORKS labels all of these things, all of these faces specifically. So if you're changing face name definitions or edge definitions, point definitions to something else, contacts look at that, and if it's not there anymore, it'll give you a little warning saying, hey, the reference is missing. So you have to go back and revisit all those contacts that were affected. The next tip, create locally applied contacts sets one face pair at a time. Very, very good practice. It is valid to go in and just group up all your face contacts into one definition, but then when you have errors or issues, you're going to have to figure out what face pairs are doing what, and that can be very troublesome. So separate, divide and conquer is my tip there. Use the animate tool and deformation scale to help with interrogating these contacts. If you look at this particular model we worked on earlier, I made sure that we had a, let's go to this one here, this example. We had a true scale there, so we can make sure that we are showing the actual deformation, that we are disrespecting that geometry. So if I decided to do like a no penetrating contact, and I go in and I look at that stress, again, we know that we're respecting that area, but because it's not a bond, the software, if I go in and I change that deformation scale so I can see what that movement looks like, it will penetrate a little bit. So again, it's wanting to qualitatively show you that. So that's a question I get asked in tech support a lot. I'm saying, hey, I get a question about that I'm not respecting the contacts in my simulation, and it happens to be a deformation scale issue. So that, keep an eye out for that. Use that to your advantage. Keep things on true scale to make sure that no penetrating contacts are being respected. Bonded contacts will be respected regardless. Face A needs to touch face B and be bonded, so that will not be affected. So if you do see an area that's not that's penetrating each other and they should be bonded, there's probably an issue. Another tip is going to be use global contacts and just leave them in there as bonded. Use it as a safety net. The idea here is when you're applying contacts, it's a good idea to go in and methodically go from left to right or top to bottom and just address all of these face pairs that you've previously detected. If you miss one, you can go in and the software, if it has a component that is not restricted or not bonded to anything, its degrees of freedom are left open. A small reaction force, a very, very small one, can just destabilize it, throw off your simulation, and you'll get an error in your calculation. So if you have globally applied context, which is the default, it will just bond that, and yes, it'll give you a little higher stress. It'll be more conservative overall, but you won't have that error message. And you can use that as a tool as well. You can turn that off or suppress it, run it, and if you have an error, that tells you that you have a component you need to address with contacts. Lastly, we have the split line tool. If you have the split line tool is a tool that will allow you to go in and segregate faces in parts, and that can be very beneficial to make your contacts more accurate. If you have maybe an epoxy that you're applying between two components and it has a specific shape, then you can use the split line tool to split surfaces to look like that shape that you need to then bond between those two shapes. Or something similar to that. So it gives you more accurate definitions for contacts. This is great for force loads as well. If you have a certain footprint for a force you can apply, you can use the split line tool to separate that face into that exact shape. It will not affect your solid body, which is the plus, but it will give you more flexibility and more accuracy in applying these constraints. So at this point, I guess we're getting close to our hour here. So if you do need to leave, I want to again thank you for coming and joining us here to talk about contacts and simulation. We will be pushing out a copy of this video, I would think in a couple of days to a couple of weeks, depending on what we're doing here. So keep staying tuned for an update on our website at DASIsolutions.com for the video, and I'll leave the rest of the time here that we have for questions. So I'll leave the floor here. I'll look at my questions box and I'll help answer any questions you may have. So I see a question here from Tomas. Hi, Tomas. What exactly is being set by selecting improve accuracy for no penetrating contacting surfaces? I believe, are you referring to the properties, the simulation study properties here? This guy, I think you are here. So what that means is if you turn that on, what's happening is whenever you apply a locally applied no penetrating contact, and if you do not do anything to the advanced setting, it's going to automatically default to the surface-to-surface contact. So again, that option you mentioned, the improve accuracy for no penetrating contacting surfaces, will default to this guy here. If you have it off, it'll just default to this guy here. If you have advanced, it'll again override to whatever you choose, but if you turn that off, it'll always override to surface. Yeah, thank you for that question. So again, I'll stick around here, and if you have questions, yeah, feel free to answer. I'll answer to the best of my abilities there and with my knowledge. So I'll be here for the next couple of minutes. All right, I'll go ahead and close the time here for questions. Thank you again for those that came and visited us here at DASI Solutions. We talked about simulation contacts. Again, we're going to be posting the webcast on our website at DASIsolutions.com, so stay tuned for that in the future, and looking forward to working with everyone in help desk and training and attending some of our training classes. Thank you very much.